Yeah, does this work? Yeah. Yeah, thank you so much. Yeah, it's such a great pleasure to be here. So the starting point of the research that I'm going to present to you today really is that famous GPT-3 paper. So Brown and colleagues chose to give this title to their paper, Language Models Are Few-Shot Learners, to emphasize this striking phenomenon called in-context learning that they found in their latest iteration of a language model, so the biggest back then. When this paper came out, myself and collaborators were working deeply in meta-learning. So we would be designing architectures and learning algorithms that could extract shared structure over tasks and thereby improve learning capabilities on similar tasks. And here comes along this paper that shows you train a big model on next token prediction error minimization on a huge pool of data, and voila, you end up with a few-shot learning algorithm that runs in context, meaning you don't even need to tweak your parameters. You just feed the model with examples, and the model will learn to solve tasks from those examples. And we really wanted to understand better how come and what this really was. And so in this talk, there will be like two halves, two parts to it. And the first part will look at toy model. So we'll try to get insights on this phenomenon on a much simpler neural network than GPT-3. And on the second part, I'll show you our attempts to use the insights that we gain to design a new neural sequence model layers and building blocks that could be alternatives to transformers. Right, so here's my outline. So first, point 1.2, I'll show you an analysis of transformers. So transformers is the transformer is a neural network that empowers GPT-3 and is currently a dominant architecture for a neural architecture for many tasks, but in particular for autoregressive sequence modeling. We'll train transformers on synthetic data and we'll analyze them the best we can. The analysis will still be not very rigorous, will still be mostly heuristic. And we'll get out of it our toy model for in-context learning. And then we'll move on to the second part of the talk, where we'll be seeing an efficient sequence modeling approach that I think has some connections to some themes explored here, or at least in the NeuroAI community. So it will turn out that we will get inspiration from local learning to design new machine learning models for sequence data. And we just finished, and the paper will appear soon. We have been trying out these ideas both in a select synthetic benchmarks, but now at scale with 1 billion parameter neural networks on language modeling to compare to the state of affairs at the moment. Okay, so to get our toy model, we will generate data synthetically. So this is a kind of a, if you want, a teacher-student setup. There's a teacher neural network that generates sequences for us. And this teacher neural network is like a recurrent neural network. And whenever we generate a sequence, we initialize some hidden state. We apply a nonlinearity, or we will also consider often the more tractable case of linear dynamics. We apply a linear map to the previous hidden state. We add some Gaussian noise to it, and then we generate some observations, possibly with partial observability by down projecting to a lower dimensional space with matrix C. So this is a very standard model in control theory and in many settings, and it's what we will use to generate our data. I think it's worth mentioning that a really key assumption we make that we take out of this, the world is large intuition. So to a first approximation, during large language model pre-training, you never really see the same data more than once to a first approximation, and in the more vanilla versions. And to model that here, every sequence that we present to the model will be generated by newly sampled A and C matrices. So we would like to not simplify too much the other side of the setup, which is the architecture. So ultimately, we'll work towards actual transformer models with a regular setup without changing them too much. And we'll optimize them online. So again, just sampling new data by stochastic gradient descent, minimizing next input prediction error. So in the same way as GPT, but here with a squared error loss, because the data is continuous. Okay, so first inspections of this toy model. We can look at how, so I'm showing here transformers with different numbers of layers. And the y-axis is the prediction error. And we can see that as the sequence gets bigger, as the model gets to know more data about a particular sequence it has to perform prediction, we see that the error drops. And this is good. So this is essentially the simplest operational definition of in-context learning, followed, for example, by Kaplan and colleagues in their famous scaling laws analysis. So the model can make sense of the sequences and use it to predict better the future. Then if you open this box, in particular, I'm showing here a very, very clean example, which is not realistic of full transformers. But if you look at a shallow model in this case, that's the first thing we looked, models just 1 or 2 attention layers. We see that the weights are highly structured and sparse. And this was suggestive of an algorithmic solution, that the model was doing something interesting inside, something very well tuned to the data. And this is just a model trained with weight decay, just a standard Adam, standard protocol, nothing special. And finally, another thing we were curious to analyze. There's been in previous analysis, we're very inspired by previous analysis by Catherine Olson and colleagues on context learning in small language models. And one phenomenon that's been reproduced and that seems to be very robust across tasks and setups is this induction head. So, and we found that in our setup as well. What is it? You look into the hidden activations of your transformer in response to the current input, and you can decode past inputs just from that current slot. I'll have a little bit more of a diagrammatic design on my next slide, but essentially the model seems to aggregate past inputs and put them together on a single hidden activation. So it starts to build a memory of the past in this way. And this, I should have said, this phenomenon was shown very nicely by Olson and colleagues in language models to co-occur with a strong increase in context learning capabilities of those models. And so we saw this as well in our toy setup. And now to give you a preview of what we found at the end of our analysis, here, as you can see in this schematic, we could like reverse engineer if you wish, the program that these trained transformers ended up implementing after training on sufficient data. And it goes as follows. So the first layers apply a nonlinear transformation to the data through these multi-layer perceptron blocks that transformers have, just standard feed-forward neural nets that are repeatedly applied to every input. And they do, just as we saw on this induction head mechanism, they bind and aggregate k inputs into an aggregate representation, where this k depends on the degree of partial observability, how much you compress with that C matrix in the generator, if you recall. And then the subsequent layers turned out to be devoted to implementing a solver in context. So the model, the main model, the transformer, ended up spawning a subsidiary model with parameters phi. This model was a linear model, and it was trained on the fly in this transformer working memory to minimize the cumulative autoregressive loss, now defined with respect to these aggregate nonlinearly transformed representations. And so, as we'll see in the next slide, this turns out to be a gradient-based solver, and we see it, we use the word, we borrow the word mesa-optimizer from Hubiger and colleagues to emphasize that it wasn't hardwired. This is just a very standard transformer. We didn't know how it would approach these problems, and it ended up developing this gradient-based technique, which anyway is very common in meta-learning. For those of you that work in meta-learning, often you have inner loop dynamics that are gradient-based. Here it's attention-based. No, not really an inner loop, just sequence processing. And it ends up being explained as a gradient-based process. Okay, so I cannot go into the details now, but the only piece of theory we have is to write down by hand. It's a constructive proof, just write up by hand a candidate algorithm. We tried a few. A candidate algorithm to do this least square solution in context. And it turns out that the algorithm that best explains the models is a relatively smart one, so uses estimates some curvature, some second order information from the specific sequence data. It's not like a shared preconditioner, it's really something tailored to the data that you're seeing for that sequence. Ends up estimating that to accelerate learning, ultimately to the point that a single gradient step then on appropriately preconditioned data would solve the problem. So it's like a smart optimizer, which it should, because these optimization steps correspond to attention layers, and we don't have that many on the transformers that we were training. So just a bit of evidence for this theory. So first we use some probing techniques. I cannot go into detail, but just training some decoders for every sequence and time point to give you evidence of this sequence-specific preconditioning of the inputs. And then perhaps more strikingly now in a quick presentation of the results, you can take these transformer models, you can vary the number of layers of the transformer models, and you can compare their in-context learning curve that we saw before to versions of our theoretical optimizer, our hand-constructed transformer, if you want, with varying numbers of layers, optimized not to fit the transformer curve, but just to do the best they can for that number of steps, and you find an almost perfect match. Finally, we find also with some probing, again, linear decoders, some evidence that after training the MLP layers, in particular at the beginning of the model, transform the data in an appropriate way for according to the MLP used in the teacher that generated the sequences in the first place. And now we can take this toy model and repeat, if you wish, the GPT-3 experiment. So this was still an unsupervised, like self-supervised trained model. And now we were curious, we are going to introduce a shift in the distribution of the sequences that we present after training. And we're going to mimic this step. Okay, here's now, after pre-training, here's now a supervised regression task. Essentially, it's still a linear task, but now with very different statistics, because you now have IID inputs and you have labels. But because this model was a least squares optimizer, it ended up performing quite well out of distribution. And so this is a toy model for this in-context learning phenomenon. And also, we tried various types of parameter-efficient fine-tuning. You can just tweak a few parameters and then close the gap to the least squares solution tweaked to these statistics. Okay, so before moving on to part 2, here's like an interim summary and mini discussion. So we got this, if you want, mechanistically interpretable model, the toy model of gradient-based in-context learning, so some kind of principal algorithm discovered by the training process, autoregressive training process. And we found that this training process instilled a very classical machine learning or statistics algorithm. You have a fixed feature extractor that it's sequence data, so binds features together, nonlinearly transforms them, and then learns a linear model, like for every sequence. This is where the flexibility comes from, on top of this, after this transform. And this is what gives rise to this good out-of-distribution generalization and perhaps good transfer properties with just a little bit of fine-tuning. And it is also like a technique in style of some corner of control theory on data-driven control, because you go around the explicit inference of those generator matrices. It's all driven by next token prediction error minimization, and the algorithm works around efficiently, explicitly representing those matrices. And here's a study from Surya's lab that I'd like to point out. We didn't analyze this in detail in our own setup, but actually surprisingly little generator diversity is needed. This paper by Alan Raventos and colleagues from Surya's group looked into this transition from an algorithm that is specialized. If you have only just a few A and C matrices, there's an algorithm, like there's a base optimal algorithm that specializes on those tasks. The transition from this to the base optimal solution from the global prior, the one that generates all possible A and C matrices, which corresponds to the algorithm that we described here. And the paper shows very nicely that a very surprisingly little amount of A and C matrices needed for the transformer to develop the general algorithm. Okay, so now for the shifting gears for the second part. Okay, so in our mind, these findings suggested a motif for designing neural sequence models. So we could just abstract a little from the specifics of that optimizer, and we could say, okay, we have, let's let the sequence specify layer-wise objective functions. So there will be some internally generated objectives that are a function of the current data. Let's then design layers that specialize on solving these internally posed optimization problems. And let's now interconnect them through some fixed nonlinearity, through some MLPs. And so here we're really trying to connect to some work we were back then also doing in computational science, and has been vastly explored in the past on these ideas of greedy layer-wise training. So people looking for alternatives to end-to-end backpropagation with end-to-end prediction error signals. There's been a lot of interest in looking into these like local learning objectives to yield alternatives to end-to-end differentiation backpropagation. And here we're really bringing these ideas to the fast sequence processing neural timescale. And there's been like success in the greedy layer-wise community. Here we're kind of like, we have a help because we still rely on global backpropagation over many sequences to figure out how to orchestrate like useful global optimizers from stacks of greedy layer-wise optimizers. So it's a little bit different from being very smart and designing by hand like a good local learning algorithm. Here to a certain degree, we can count on backprop for doing that to us. And there's, before going to the details, maybe just a bit like why are we going to do that? Maybe in reverse order, like first it's a way to indirectly validate our toy model findings in realistic data. We were never really able to, and didn't try very hard to be honest. We're not very hopeful of analyzing like language models and finding traces of our mesa-optimizers there. And so this is like an indirect way to build on those findings in the realistic domain. And also, as we'll see next, we were hoping of contributing to this exciting wave of research on alternatives to transformers that are in some way better. And along other axes of what better may mean, we will look into better in terms of computational efficiency to see if this local learning can help us get around one of the major problems of transformers. So just a very quick recap of the basic building block, the sequence processing building block of a transformer. It's a softmax self-attention layer. And in this schematic, I'm just recapitulating. So there's a sequence of inputs to the model, to this layer called E, indexed by time. And every time a new input comes, a new ET comes, you produce these queries, keys, and values with some linear maps. And the thing is, with attention, you have to explicitly keep in memory the previous keys and values at test time. So whenever you are doing inference with these models, the world is ticking, you're getting more data, you need to have these growing lists of keys and values and compare the query to all of them so far. So this gives you this tricky problem that per time step compute and memory cost grows linearly with time. And there's been a wave of research and with very many details. And I think this captures the gist of it. It's like a resurgence of RNNs, or now also called state space models. And the most powerful ones, at least in my view, have this motif in common. So the basic insight is, let's just drop the softmax nonlinearity. So if you drop the softmax nonlinearity, you can now use associativity and just group things together differently. And so now things change drastically, because you can still compute in parallel, which is very useful for training these models at scale using current hardware on GPUs and TPUs by just keeping the matrix expression as before. But you can now do something interesting at test time. You can unroll these models recurrently, so they become an RNN. With an interesting point that the state of this RNN is matrix valued, and turns out to be a sum of outer products between values and keys. Before going here into details here, just the obvious thing is that now compute and memory cost per time is now constant. Okay, so since we are in NeuroAI community, I have to say, when I realized this clicked, it gave me a lot of pleasure, like to just connect that old school research from the 1960s and so on associative memories with transformers. So it turns out that these outer products, values and keys, is just plain old Hebbian learning between associating keys and values, which goes really back to venerable research in computational neuroscience on heteroassociative memories. So that's really all that is happening under the hood on these RNNs. And this is the key idea behind many recent recurrent neural network alternatives to transformers. On the other hand, without going too much into details, there's also a beautiful connection into so-called modern Hopfield networks on the softmax side of things. But one easy way to think about it is just like really some kind of soft nearest neighbor memory retrieval matching using some similarity kernel based on those dot products. Okay, so what we're going to do on top of this research is, instead of relying on plain Hebbian learning, which is known to suffer from like generalization and memory capacity issues, it's like a limited learning rule. We're still going to keep that matrix formulation, keep a matrix state, but we're now going, inspired by our findings, we're now going to obtain it through explicit optimization. So this is like a form of test time optimization. For every sequence, each one of these layers will solve a little least squares problem. We are free to design how it will solve it. And I just wanted to mention we do some generalizations from our automatically discovered algorithm. One of them that I think is most interesting is we want to stack these layers. We want the power of deep learning. And so we will let backpropagation generate the rules that specify the targets for each layer. So these values play the role of labels or targets, and they're really dynamic. They depend on the sequence, and they are internally generated. So each layer will do some computation, will solve a problem, fit this, pass something to the next layer, and part of it will be, hey, here's the data that specifies the next subproblem that has to be solved. And we also do some minor improvements, like adding a forget factor to allow the memory to erase. And so there's really a shift in perspective here from pure memory, associative memory, to really trying to learn, you see it also in the crucial use of regularization, trying to learn patterns from the sequence data. It's really from memory to learning once we go optimization. And so here's the layer, just writing it down. I won't go in too many details, but it turns out to be that you can express one possible way to solve these efficiently is to express, to keep a matrix valued state, one that corresponds to the linear attention one, and then on top of it, this additional H variable, and then you can really, at every time point, call your solver of choice to solve a system of linear equations. And you can, again, has this nice property. You can do this in parallel to do fast training, but also recurrently at test time. And we use the conjugate gradient method in our case, but perhaps other choices can be more appropriate in different circumstances. And so we're going to insert these mesa layers, as we call them, in standard architectures. So we just take an architecture that is very close to the llama transformer from our colleagues and collaborators and the so-called Griffin model published last year. And we will stick with it and do all our related work comparisons ourselves in this common architecture, which is very close to a transformer architecture. Okay, let's go to the experiments. So first we attacked two suites of synthetic benchmarks, one from Polly and colleagues called MAV. It's a series, so here the model is trained on these synthetic benchmarks. It's not trained on language, we'll see that later. And it's I won't go into details, but it's a suite of, we think, well-motivated toy examples that are relevant for things that LMs presumably do. We train a bunch of models. Everything that I'm going to present was in-house trained for all the experiments and in-house hyperparameter optimized carefully for the different models to really make comparisons meaningful. And we see here that the mesa layer, here comes that table of numbers where the model performs well. The mesa layer is a good model across these suites in comparison to the top state-of-the-art RNNs. This is an interesting benchmark interest here around the corner at MIT, RegBench by Akurek and colleagues. So here you train, you generate languages using some family of automata. And so the key point is it's an in-context learning benchmark. So at test time, you'll need to apply your model to new tasks, newly sampled languages. It will need to learn this weird gibberish language at test time. And this is where we see also quite significant gap to previous work, again, in line with the powerful in-context learning capabilities by design of our layer. When it comes to actual classical language modeling perplexity, the perplexity metric, so now this is, we switch gears to a big model. It's like a 1B parameter model trained on 50 billion tokens on sequence length 2000. And we see here that the model does push the state of the art a little bit forward. So we compare to the top RNNs. And I think that's good. It's not like a table of like a massive improvement or destruction of the related work. It's like a progressive improvement. But there's a couple of things that are interesting that I want to dig into in the next 2.5 minutes, which is that these models are actually the best of them, in particular, this Hawk Mesa, I'll describe what it is in a second, are actually better than transformers. So you may be, or really on par with transformers. So you'd be like, wow, this is like really incredible. And in a way it is, but this prompted us to be a little bit more detailed in our analysis. And we found something quite intriguing that is not really related to the mesa layer, but it's really a finding characterizing the current field of this wave of efficient SSMs and RNNs versus transformers. So it turns out that when you look at the cross-entropy loss at different token positions, so you can repeat this analysis of let's give it longer and longer sequences, and you compare these models to transformers, the way they actually achieve these very impressive perplexities is kind of surprising. So they actually beat transformers. So how do you look at these numbers? 0 is the comparison point. It's the transformer performance. If you're below transformer performance, that's below the curve, that's good. If you're above the curve, that's bad. Means that the transformer is beating you. And you see this interesting curve. So the mesa layer and other top RNN models end up being better than transformers at short context length. But you start to see their deficiencies in longer contexts. So they achieve better perplexity in different ways. And intuition tells that this might not be really the right ways we would wish for our models. So transformers really have this special property of managing long context very well, which, given that they store everything, might not come as surprising, but still, it might be a key property. And it's good to know that current RNNs, this is being masked in the perplexity. They're not quite there yet for longer contexts. Last point I wanted to show you is with this local learning optimization-based approach, you can actually play some games with test time compute. And in particular, this offers you a principled way for a variable compute allocation at test time, sequence-specific compute allocation. And it's just because a solver has, you can apply to a solver a dynamic stopping criterion, depending on some desired error level. And for some easier sequences, you hit it quicker, you spend less compute. Harder sequences, you may need more steps. And it just adapts on the fly, which we think is an interesting property. And you see that indeed, for longer sequences, perhaps unsurprisingly, you need more benefit from more compute. So it's hard to find like a static criterion that works both for short and long. It just as an example of the usefulness of this idea, whereas the dynamic stopping criterion allows you to recover good performance. Maybe just one quick remark. I don't have more time, but you see also that in reasoning benchmarks, you benefit, especially in harder reasoning benchmarks that require long context. You see that this extra compute is needed and can be automatically done for you. Okay, that's it. So just a very brief summary. We've seen a mechanistically interpretable toy model for in-context learning, mesa-optimization. There's been a lot of follow-up, beautiful theory work on top of our heuristic analysis, putting this in more rigorous terms. We propose this mesa layer, and this really comes for us as one candidate of this space of ideas that come from using local learning to fit sequences and build neural sequence models. And we saw that this layer has strong performance, competitive performance, so the idea makes sense because it's actually the best out of the current generation in language modeling. But careful that transformers are still in many ways special, potentially, and in particular, we saw that in the way they handle local. So thank you. I just really want to say big thanks to Johannes, the mastermind of this research and the lead developer of the model, Max, who did all those interpretability analysis, Nino, who did all those careful and smart evaluations, and Blaise for being our inspiring principal scientist and co-researcher, co-conspirator. And long list of people involved in this research. I just wanted to quickly mention our paper with the language modeling results is about to come out, I think tomorrow. We submitted it just a few hours ago to arXiv. And we'll release some collab notebooks and different like Jax, PyTorch, if you want to build on these ideas of local learning, and also an efficient open source Triton implementation from Songling Yang. Huge thank you at MIT, who developed it for the open source community. Thank you.
It was an amazing talk. It was really amazing work. I was hoping to give you a chance to like talk a little bit more about the associative memory network aspect of the MESA-net and sort of give more in-depth information about that, because I've been working with them and I find them very cool.
Okay, thank you. Thank you so much. That's really kind. I wanted to say there's something I think special about this here. Actually, something, if you keep in mind, we want an efficient system with constant compute costs and memory per time step. I think something magical, if I may say, happens here, because this objective actually sums back in time potentially to the beginning of time. So naively, one would expect you need to store all these states in memory, like the transformer. But it turns out there's no miracle. It's just Gauss solved it for us already. It's just this recursive nature of like least squares problems. So because this is a quadratic cost, there are ways to approach it that go back at least to Gauss. They're efficient and that allow you to. And so returning to the memory point, it's also in some sense, it is the optimal linear associative memory. So it is in the squared error sense. So it really memorizes keys and values in the best possible way according to squared error metric. Yeah.
Thanks for the beautiful talk. Am I making a false connection here that maybe you've solved some of the problems that seek to seek actually started out with, right? That was sort of the precursor to transformers, and then people didn't, from like now Kalkbrenner, right? And then in some sense, like the problem was that it just wasn't efficient, but this seems like a really elegant solution to that.
I have to say, like, I feel like it's justified that I think of myself as a computational neuroscientist. I'm too new to the field to know exactly what the seek-to-seek problems were. But like, yeah, so we're really trying to target, the dream is, and we're working also in our team on problems involving reinforcement learning with self-supervised learning, as Surya also mentioned at the end of his talk. And here, like, long context processing is really, really important, and you have to do it efficiently. And so for us, this efficient long context processing is key, and that's really one of the reasons why we decided to scale up this research and see how well these layers work.
Yeah. That's very cool.
Thank you.
Great analyses. When we've looked at transformers, at least early layers of transformers, one thing that seemed really critical was the positional encoding. And if you take them away, especially in simple toy cases, you break all of the interesting stuff. So do you think that positional encoding is a critical ingredient here, or is that something that you've looked at?
For the toy experiments, for sure. You need to know, again, also to copy together things and everything. For these recurrent neural network models, it's more delicate. Maybe it's a good question for Johannes. Maybe he would have an intuition here. I don't have personally any very good intuition. But for the toy transformer analysis, for sure, they are really critical. Yeah. Yeah. But for RNNs, you don't necessarily need them, so it's another story.
Thank you for the great talk. The question is, this might be a little bit too much of a nitpicking for the first part of the talk, but if I assume that the first layer of the transformer is doing a heavy lifting in separating the input signal to a well-defined and orthogonal individual channels, then technically the late layers, the preconditioning matrix H, that could be almost diagonal, right? If the first layer is already doing a heavy lifting. So I was wondering if you looked into the structure of the preconditioning matrix that is calculated by the later matrix, and if it was actually diagonal or more close to just a dense.
First of all, here, thank you for the great question. Like the actual generative model, like the prior from which you're sampling these sequences matters, like what's the optimal preconditioner. It comes also, depends on the prior, the task prior or the sequence prior. Just to say the algorithm that we discovered in our reverse engineering would really need multiple steps of attention to gradually improve this preconditioning. So it would be surprising if the first layer already did a lot of the work, and it would really be, I think, it could only be explained in relation to the task prior. So maybe for certain priors that's possible, but I would say not in general, according to this algorithm.
Hi, thank you for the talk. I was just wondering, in the original mesa-optimization paper by Hubinger, there was like quite a bit of concern about mesa optimization bringing about inner misalignment. And I know we're not at a safety symposium here, but I was wondering if you could maybe speak a bit about any kind of work at Google that may be addressing the safety concern of mesa optimization.
I cannot speak for the broader work at Google here. Just with regards to our particular findings, yeah, we actually think it could be a useful toy model if you now couple it with reinforcement learning on the outer loop. It could really provide a decent starting point to analyze the appearance of these inner objectives. And how they might be optimized. And also, once you start using reinforcement learning to keep on stepping out of the distribution, how these solvers may be used. And again, we have these like internally generated targets and what they may be. But of course, like I think it's potentially a very interesting toy model to start working with and try to answer those questions. We did not do it specifically yet ourselves. And of course, in the current context, the objective is very well aligned with the outer objective by construction. You're like, again, we're relying on backprop to solve that outer objective, and the inner objective we find is very well aligned with the outer objective, just to be clear. So here, I don't think there's any direct sign of that, but it could be a good starting point. And I think in particular, once you also have RL on the outer loop. Yeah.
around next week. Thank you so much.
Thank you.